I will do a quick review of what Dr. Senga talked about last class. So it's basically interpolation, and so if we have one element and this is x, and normally what we do is that we have a reference coordinate s from 0 to 1, and the given information is deflection and rotation at node. So it's v1 theta 1, v2 theta 2 at 2 nodes. So for this interpolation, we use a cubic polynomial. So why we use cubic polynomial, not higher order? Yeah, because we only have 4 information, and in this cubic polynomial we have 4 unknowns. So that's the only way we can solve this. If we have higher order like the 4th order and C4, then we will have 5 unknowns, but we only have 4 information. It's impossible to solve this problem. So using this cubic polynomial, we have the information when s equal to 0, vs equal to v1. When s equal to 1, at this node, v1 equal to v2. And the third information is the rotation. So when s equal to 0, dv, we know that rotation is dv over dx. So dv dx, s equal to 0 equal to theta 1. And dv dx, when s equal to 1 is theta 2. So these are 4 information given. We can use these 4 equations to solve C1, C0, C1, C2, C3. So this interpolation, we can reorganize and write it in a way that V1, NS, N1, theta 1, N2, V2, N3, and theta 2, N4. And if the students took notes in the last class, you may find that Dr. Senga put L here and put L here, right? Check your notes in the last class, because I watched the video this morning and I found that he has L here and L here. So because in the shape function, we have L here and L here in the N2 and N4. To be consistent with the slides and textbook, I decided to remove this L here and here. So it's V1, N1, theta 1, N2, V2, N3, and theta 2, N4. So by calculating this, we can find the shape function is N1 function of S, N2 function of S, N3 function of S, N4 function S, and the highest order is cubic. And if we plot this 4 shape function, we can find that it looks like this. So we can check if this result is correct. So when for N1, when S equal to 0, N1 should be 1. So here, the other should all be 0, and V, when S equal to 0, it should be N1, V1. And also for N2, it should be at this node, S, this is S equal to 0, this is S equal to 1. At this node, N3 should be 1, and all the others should be 0. So this should be 1, all the others are 0. So at node 2, when S equal to 1, V should be V2. And also check the N2 and N4 for the rotation. When S equal to 0, S equal to 0 here, and if you take a derivative first dv over dx, you can find that only this N2 over L, the slope here is 1, and all the others should be 0. So theta 1 dv dx. And same for N4 here. When S equal to 1, this slope should be 1, and all the others should be 0. So this is the shape function and interpolation, cubic interpolation, the basics. And so I will give an example problem how to use this interpolation. any question in this part? Okay. The example problem is that I have a cantilever beam. And this node is V1 theta 1. And this node V2 theta 2. And for the given degree of freedom, it is 0, 0, so the question is how to find out the deflection and the slope at x equal to half of L at the midpoint. So this is L. So this is the question. A cantilever beam and clamp on this side, and the Q is given as 0, 0, negative 1, negative 0.1, negative 0.2. And the question asks, what is the deflection and rotation at x equal to half of L, so at the middle point? How to solve this question? This is a very typical interpolation question. So how to do this?
You just use your shape function here.
Use shape function here.
And plug in your s equals 1/2.
Yeah. Yeah. And then use this one, right?
Yeah.
So because we have this, so this interpolation function means that once we know V1 theta 1, V2 theta 2, we can calculate the deflection at any point on this element from 0 to 1, as between 0 to 1, we can calculate any deflection and rotation on this element. So now we know that if we define this as s equal to 0, this as s equal to 1, this in middle point x equal to half L, s should be equal to 1/2, right? So we put the 1/2 here, and V1 theta 1, V2 theta 2 is already given here, right? So because this side is clamped, the deflection and the rotation on node 1, V1 theta 1, 0, 0. And this one, V2 theta 2. So here we can see that for this problem, Vs, so V1 N1 theta 1 N2 V2 N3 theta 2 N4, right? But because this is 0, V1 theta 1, 0, we can delete this two part, and then we have V2 theta 2, and for N4, N3, N4, we put s equal to 1/2 into the shape function, and then we can calculate N3 half, N4 half. So this V at middle point can be calculated, right? Any question here? So I calculated the deflection at this middle point. The last question is that how to calculate rotation at this middle point. the theta, deflection, and theta. So we know that the definition of theta dv over dx, right? Is this correct? Theta equal to dv over dx. And because we know that v here is a function of s, so we need to use the chain rule to change this to dv ds ds dx, right? And so we can use that interpolation function to calculate this part. What is this part? ds over dx. 1 over L, right? This is x, and the length is L. And in the reference coordinates, S1, S equals 0 here, and S equal to 1 here. So this ds over dx 1 over L, right? So this can be calculated as 1 over L, and then the dv ds. So for theta, when s equal to half, we can calculate it as the same, because same here, v1, theta 1, 0, we can ignore this two part. So start from v2, theta 2. So it is v2 n3 half prime, theta 2 n4 s equal to half prime. So this is a rotation at middle point. And because since we have the n3 and n4, we can calculate the n3 prime at s equal to half and n4 prime when s equal to half, and then plug in the v2 and the theta 2. So this rotation can be calculated. Any question here?
On the top equation on the right-hand side of the board, the third derivative from the left, what is that symbol? There's this theta is equal to dv dx on the upper right-hand side. Was this theta is equal to dv dx is equal to dv over ds times something over dx?
ds over dx.
ds over dx?
Yeah. So this is a chain rule of differentiation, because this is the definition of rotation, right? dv over dx is only defined in the x coordinates. But because our v is defined in reference coordinate, s coordinates, v is here. So we need to think a way to connecting these two. So what do? That we use the chain rule differentiation, dv over dx equal to dv over ds over dx, right? And ds over dx is equal to 1 over L. So, and for this part is just simply put, I should write it, dv over ds should be v1 prime theta 1 v2 and 3 theta 2 and 4 s prime, right? So this is dv ds, simply from that function, interpolation function. And because in this problem, v1 0, theta 1 0, so these two terms can be ignored. We only consider this part. And this part, we already have V2 theta 2, V2 theta 2, and then you take, calculate these two parts, dn3 ds and dn4 ds, and plug s equal to 1/2 into it. Then you can calculate this rotation at midpoint. Any question here? If you have confused about any point, you can just ask, because I'm more about that. I didn't explain it clearly enough. Any question? So this is the interpolation function. If no question, I will move on to the second part is energy. So I think Dr. Sanka already talked about that strain energy, the definition of one element. The strain energy of one element is UE equal to EI x1 x2 dV dx. dx. So this is a definition of strain energy of one element. The same, we need to convert it into the reference coordinate, s coordinate. So at this node s equal to 0, at this node s equal to 1. So to convert it to the s coordinate, it can be written as change this x1, x2 to 0 to 1, because s coordinate is always 0 here and 1 here, and this ds here, and because dv dx equal to dv ds dx, so you have like for this part you have L fourth order 1 here, and then because dx equal to L ds, so you have 1 more here, so this is why this cubic come from. So because this is just a review of the content last class, I will do it quickly, so if you have any question, just ask. So this is in s coordinates, and I think he also covered that for the vs, dv ds. This part can be written as n double prime, n2 double prime, n3, n4, q. Right? n1 v1, n2 theta 1, n3 v2, n4 theta 2. So this is the dv ds. second derivative. And also, this can be also, written as V1 theta 1, V2 theta 2. To make this less confusing, I will change this to V1 theta 1, V2 theta 2. So we can either calculate it in this way, or we can calculate it like this: N1 double prime, N2 double prime, N3 double prime, N4 double prime. Same here, dv ds. So for this part, we can put it in a way that okay. For this one, we can write it as we simply put this, use this two, and put this one to this one here. So this is a row vector, column vector, row vector, column vector. So this is the square here. And for this part, we can see that this is 1 by 4 row vector, and this is 4 by 1, and also this is 1 by 4, 4 by 1. What we can do is that we move the Q outside, and if we move the Q outside, it should be QT outside. We can see that for different element, for different loading condition, boundary condition, this Q different, EI different, L different. But for this part, it should be always the same, right? Because when we use the S coordinate, S always from 0 to 1, and no matter what your loading condition, boundary condition, everything, this should be always the same. N is always as a function of S, and S is the reference coordinates. So we can define this as the stiffness matrix K. And for all the bin elements, we should have the same stiffness matrix, right? Any part that is not clear to you?
I'm so confused where the L cubed came from when you went from the first to the second line. I get that dx is LDS, but where did the L squared?
Where's which one?
Never mind.
Oh, this one?
Yeah.
Because dv ds, there will be L, and square here, there should be L4, right? And this dx should be L ds, right? So this one and this one give you,
Okay.
yeah. Any other question?
Just double check, but for the direct line, is it supposed to be beta 2, right? Under U2. It's like U1, beta 1, U2, beta 3 for the direct equation.
Third equation, this one?
On the last.
Is it supposed to be theta 2 instead of theta 3?
Oh, sorry. Thank you. Theta 2. Yeah. Any other question? So, after write this strain energy of this spin element, we can define this part as a stiffness matrix, and this part should be the same for all elements. Now we can. So since we already have the shape function n, n1, n2, n3, n4, and because this is a column vector, this is a row vector. So what should be the size of this one? This two product. What should be the size of this one? 4 by 4, right? Because it's like this. N1, N2, N3, N4. And then you have N1, N2, N3, N4. If you calculate this one, it should be 4 by 4 matrix, right? Correct? So you can do the calculation yourself after class if you have time. And I will just give you the result directly. And in the exam, you can use this stiffness matrix directly. You do not need to derive it during the exam or homework. So the stiffness matrix should be, I think it's in the, okay. So, I forgot, this part also included in the stiffness matrix. So K should be equal to EIL cubic. So to correct what I just said, stiffness matrix should include this EIL cubic in the stiffness matrix. So this is the same for all the elements, but this is different for each element. So stiffness matrix can be written as this one. And in your exam or homework or any problem in future, you can use this stiffness matrix directly. You do not need to derive from here because it takes a lot of time. And so this is, I think, what Dr. Sang covered last class. And now we have the strain energy. We can calculate the potential energy for external forces. So to simplify this equation, I can also write this strain energy of this element as 1/2 Q T K Q, right? And this is for one element. And for a system, if you have multiple elements, you can write it as U equal to from element 1 to total number of element, and this is for one element. 1/2 Q transpose, this part is stability matrix, K for this element, and Q here for one element. And for a system with multiple elements, we can just add, because strain energy is a scalar, right? We can add them together. So from element 1 to the total number of elements, we add them together, and then we have this equation. QS, KS, QS. This delta transpose here. So this is a structure stability matrix. Do you remember what is a structure stability matrix? I think this is the same. This concept is the same in your trust problem. So structure stability matrix means that you assemble everything, but you didn't apply boundary condition. Remember? And after you apply boundary condition, you delete rows, delete columns. It is called global stability matrix, right? Yeah. You should remember that. It's the same thing in your trust problem. So this is strain energy of the beam problem, and now we calculate the external potential energy of external force. Potential. So for example, I have one beam element, and I discretize it like this. And then for this is node 1, node 2, node 3. It's too much. Okay. And at each node, I have F1, C1. F2, C2. I'm saying here F6, C6. How to calculate the potential energy of these external forces? I think you learned this part before. Potential energy should be, there's always a negative sign here, and should be F1 multiplied by deflection at this point, V1, and then C1, the couple here, and theta 1, right? I'm saying for node 2, F2, V2, this is deflection. C2, theta 2. And same for F6, V6, couple at node 6, rotation at node 6. Is this correct? So any problem here? The potential energy of external forces. You have the concentrated force and couple at each node, and then you calculate the potential energy of all these forces and couples. So for this one, we can always write it in the form like in this part. So it should look like V1 theta 1, V2 theta 2, V6 theta 6. And then this is a row vector. I can write here as F1 C1, F2 C2, F6 C6. So these two are the same, right? I just write it in different form. This is a row vector, this is a column vector, this is all the degree freedom, and this is all the forces, external forces, right? I multiplied it by this one, I get this one. So these two are the same thing, just different, written in different form. So by written in this way, what we can do is that the total potential energy should be the strain energy plus the potential energy of external forces. And for the strain energy, we already write it at this one, and I can put it here. So it should be 1/2 QS KS QS. And because the potential energy of external force will have a negative sign here, so we put negative sign here, and it is QS transpose. So it's a row vector here, QS transpose, multiplied by FS. So this one, external forces. Right? Any question here? Now we should know that for all the QS, the V1, theta 1, V2, theta 2, V6, theta 6, there should be one set of Q that make this total potential energy minimum, right? You should minimize this one. How to minimize this one? How to minimize this total potential energy? Yeah. Total potential energy, all the variables, it's like V1 should be equal to 0, total potential energy, theta 1, 0. Right? So this is the requirement to make this total potential energy equal to 0. So by doing this, we can find one set of this V1, theta 1, V2, theta 2, V6, theta 6 to make this total potential energy minimized. So I think in the chapter 0, there is a equation that to find Fx equal to 1/2 x a x you can check your textbook later after class. So to find the minimum of f, this x should satisfy this one. So this is more like 1/2 a x squared equal to bx, and to find a minimize of this value, it should be satisfy this one. So when you calculate this one, it should be the set of value, the variables that make this one to reach the minimum. And the same here, we can use this. This is the equation, mathematical equation in the chapter 0. And the same, we can apply this one to here. So this equation should look like K Q equal to F, right? Use this one. This equation is the same form as this one. And if this equation can minimize this Fx, and this should make this total potential energy minimized, right? So by calculating this one, I can find one set of V1, theta 1, V2, theta 2, everything to minimize the total potential energy. And that is the result we need. When we apply boundary condition, everything, and apply the loading condition, we can find the deflection at each node, rotation at each node. That is the result we need. Any question here? But one problem here is that I just said QS is the structural stiffening matrix. So what's the problem of structural stiffening matrix? Same thing in your truss problem. It is singular, right? Before we apply boundary condition, the structural stiffening matrix should be singular. It has so you can check in your textbook later. This QS should be symmetric and singular, and because this one is singular, there's no way we can calculate this one, right? Because we can not just like no, K is singular. When K is singular, we cannot calculate QS. So what do we need to do? This is irreversible. What should we do? Apply boundary condition. Apply boundary condition to make this one determinant not become 0. So we can calculate this one as QS as now. After we apply boundary condition, we can inverse and FS, right? Apply boundary condition. So this is the basics in this energy part, and I think I will do an example on this part. Let me see. Any question here? The basic theory, the strain energy of element and external potential, the potential energy of external force, and total potential energy is the we add these two together, and how to find the minimized total potential energy, and then we can find the Q, the V1 theta 1, V2 theta 2, V6 theta 6. Any question here? So if no question, we can do an example problem. So this is a beam and clamped on both sides, and I have a force at the middle, 240, concentrated force, 240 Newton, and this is 1 meter, this is the 1 meter, and what else? That's it. So the first question is to calculate the deflection and rotation at this point, the loading, the node that we applied this 240 Newton. So how to do this question, how to solve this question? First, what do we need to do? What is the first step? Discretize, right? How to discretize? How many elements should we use? 2? Okay, yeah. Why 2 elements?
So you can place a node where the force is.
Can I do this?
There's no boundary condition.
What?
I was just going to say there's no boundary condition there, but it's just 0 force. So there's
Boundary condition is clamp here and clamp here. Loading condition is I have concentrated force at middle node. And the first question is how to discretize this one. Should I use, like, at least I need to have one node here, right? Because I need a node to apply the force. And should I use like one element here, or more elements here, more elements here. What should I do? I think this is the same problem in your abacus homework. So it's kind of like I partially solved your homework problem. It's 2 elements or more elements?
The more elements you have, the more accurate it is, like in each location.
Okay, that's one answer. Any other? So, as I said, for different loading condition, if it's concentrated force, the exact solution deflection should be a function of x cubic, right? And I think I talked about this in the abacus tutorial. If it's distributed force, constant distributed force, it's like constant distributed force, this deflection should be x 4th order. And if it's linear change distributed force, this Vx should be x 5th order. And I make it complete. If it's a bending moment, it's a couple, just apply a couple. This Vx should be x squared. Do you remember this? I did this in the abacus tutorial. So, because in finite element, we always use cubic polynomial, right? We always use cubic polynomial. So, for these 2 cases, finite element can give you accurate result even with 1 element, right? Because it has the capability to do this. If your highest order is square or quadratic or cubic, and my interpolation function is cubic, it means that my interpolation function can give you accurate result. Just use 1 element. But if the accurate result is 4th order and 5th order, but I only use the cubic to do the interpolation, it means that finite element will only give you approximation. And in these 2 cases, more elements, the better. Understand? Or any question can ask.
How many elements though is ideal? Like more elements is better, but like at what point do you notice?
In your abacus homework, probably I don't expect that you use a large number of elements because there is no restriction in your student edition. And for a reasonable discretization, probably 10 is enough. Yeah. So back to this question, how to discretize this one? It should be 1 element here and 1 element here and give you accurate result, right? Anyone still confused? Okay. So. So, because for concentrated force, the exact deflection should be x cubic, and because our interpolation function in finite elements is also cubic, so 1 element can give you accurate result. So I can use 1 element here, 1 element here, so I can define this as node 1, this is node 2, and this is node 3. So this is the first part. Now, I have 2 elements, and I have loading condition, bounding condition, everything, how to calculate the deflection and the rotation at node 2. Think about your truss problem. We have to use this one, right? K, Q, F. K, Q, so it should be find out the stiffening matrix for element 1. For element 1. I think I wrote, okay, here. Use this one. As I said, you do not need to derive this in your homework or exam. You can just use this directly. So let's see how to use it. For element 1, okay, I forgot 1. EI equal to 1000 region. For element 1, the stiffness matrix should be EI equal to 1000, L equal to 1, right? For element 1, L equal to 1. And then I have 12, 6, negative 12. So this is stiffness matrix for element 1. Any question here? I just use this one directly. And we can do the same thing for element 2. Oh, time's up. I will continue next class.